Okay, so if you finished the last video, you probably wondered what happened, and I just got distracted and cut the video off. Rather than redo that entire video, I think it's easier just to pick up where we left off. If we can just pretend like nothing happened there. What I had just finished verifying at the end of the last video is that when we have xy, which was 2, 1, right, if we had 2, 1 in the relation, then in order for this to be symmetric, we also have to have the element with these two guys reversed, and 1, 2 is also there. We see that right here. So for every element that we see, if we randomly pick one element in the relation, then do we also see another element where the x and the y are reversed? And that is true in this case, right? So it would be, if we think about what would we have to change to make this not symmetric, well, that would be pretty easy if we just kicked one of these guys out, right? So if we kicked, say, that element out, then this relation would not be symmetric, because if I choose 1, 2, I would be missing the element with the x and y switched around, right? So if this one hadn't been there, the relation would not be symmetric. Right, okay, so a similar idea is that of antisymmetric. And what I've done is I've written this definition a couple different ways. So this is the first way. So it's a similar idea to symmetric. Of course, antisymmetric hints that it's not quite the same. Right, so, and then a second way we can think of this is that way. Either way is fine. Sometimes it's easier to use this second definition. It's easier to think in those terms. But so what antisymmetric says is so when we were looking to see if our relation here was symmetric, we picked out one element, and then we scanned through and we see if we can also find the element where the x and the y are reversed. Well, for antisymmetric, right, the if part of the statement says if x is related to y and y is related to x. So, for example, we've got some case where, say, 2, 1, 2, 1, and 1, 2 are in the relation. Of course, we're going to see that that doesn't work, but that's what the first part of this definition is saying, right? We've got this element in the relation and this element in the relation, but then we have to conclude that x equals y, which of course wouldn't be true for these two. Right? But just to illustrate a little bit of a difference in the definition. Or another way you can think about it, and this is just taking the definition and writing it in the contrapositive. So if not this part, so if x is not equal to y, then not the first part. So then either x, y is not in the relation, or y, x is not in the relation. Okay, so so I've got a example of a relation here that is antisymmetric. So let's think about this first form of the definition. Right, I went ahead and wrote this. I went ahead and wrote that example up there. If we look at the relation, here, right? In order for this relation to fit the definition of antisymmetric, right? This definition is an if-then statement, and that's true when, right? So remember we had a truth table for P implies Q. Right? That was true if the if part and the then part were both true, or if our hypothesis, the if part of the statement, was false, then this statement is true by default. Right? Well, if we look at our if part, I've got a element here where xy is in the relation, but yx is not in the relation. That means the if part of my definition is false, and if the if part of my definition is false, then the if-then statement is true by default. Right? So this if-then statement is true, which means this relation is antisymmetric. Maybe looking at this second form of the definition makes it a little easier because of the way it's stated. If x is not equal to y, okay, well, if we start looking at our elements, here x is equal to y, here x is equal to y, here x is equal to y, so I would only be focusing in on this element where x and y are not the same. And then is it true that either xy is not in the relation or yx is not in the relation? And yes, we can see that because we're missing 1, 2. If either one of these is not in the relation according to that, then our relation must be antisymmetric. So either way you look at it, this relation is antisymmetric. Okay, so how would a relation be not antisymmetric? Well, let's go ahead and rewrite this out. If I throw this element into the relation, right, so if I look at the relation now, which is how it was in the last example, right? Remember in the last example we were showing that the relation was symmetric, so it might make sense that if the relation is symmetric, then it's not antisymmetric. Right? Now this relation is not antisymmetric because it is symmetric. We saw that in the last example. Right? If I maybe look here at this second form, maybe it was a little easier to think about. Right? So if I look at this element and this element, because that's where x is not equal to y, then can I say either xy or yx is not in the relation? Well, no, I can't say that this is true because they're both of these, xy and yx, 2, 1 and 1, 2 are both there. So this relation is not antisymmetric. In fact, in the last example, we saw that it is symmetric. And that seems to make sense. But there are some subtle situations where you do have to be very careful. For example, if we have this relation, again, this relation is antisymmetric. This relation is antisymmetric because it fits. I think in this case it's maybe easier to look at the first form of the definition, right? Because if x, y, and yx are in R, well, that's true for all of these, right? Because again, when I try to reverse the elements of 1, 1, 2, 2, or 3, 3, I get the same element. So I've got x, y, and yx both in the relation, then x equals y. And of course that's true. That's true for all three of these elements in my relation. Or if I look at this second form, the hypothesis part of my definition is false, which makes that definition true by default. So either way I look at it, this relation is anti-symmetric, but if I go back to the definition of symmetric, it is also symmetric, because if so say I take this element, right? Say I take this element and I try to fit to the definition of symmetric. If 1, 1 is in the relation, then I would be asking, is 1, 1 also in the relation? And it is. Right? If 2, 2 is in the relation, then I'm asking, is 2, 2 in the relation? And it is. Right? So this is kind of a funny relation where it is both anti-symmetric and symmetric at the same time. Right, so the reason I mention that is because you can't just automatically say, well, since my relation is anti-symmetric, it cannot be symmetric. Normally that would make sense, and normally that would probably be the case, but not always. You might have a weird case like this where your relation is both anti-symmetric and symmetric. Okay, and then there's one final property of relations, and we will look at that, but I think I'll do that in a separate video.